Hello, I'm Görkay, and I will be presenting our work, Real-World Point Tracking with Verifier-Guided Pseudo-Labeling. Our task is point tracking. You are given a single query point at some frame, and you have to follow this exact physical point through the rest of the video, predicting both where it is and whether it's visible. It's a primitive that shows up everywhere: video editing, 4D scene understanding, and robotics. Here is the issue. Trackers are trained on synthetic videos, like top with Kubrick, because that's the only place you get dense, frame-accurate ground truth. This kind of data looks like this. But when you deploy them on real videos, performance drops. Real footage has different appearance, motion, and occlusion patterns, and you don't have annotations to fine-tune. So you see a clear gap between the training and test domains, which raises the question: how do we train on real unlabeled videos without ground truth trajectories? The standard answer is pseudo-labeling. You take a pretrained tracker, run it on real videos, treat its predictions as labels, and fine-tune a student on those. Prior work essentially follows this pipeline. Given a real-world video, to fine-tune our tracker, one teacher is picked, sometimes randomly per video, from a set of pre-trained trackers. And we just trust it. The output of this tracker becomes a pseudo-label. But that raises an obvious question. How reliable is a single dice roll teacher? Turns out, not very. Here is the same point tracked by 6 different state-of-the-art trackers across one video. Predictions vary frame to frame. A tracker that's accurate at frame 50 might drift completely by frame 130. And different trackers fail in different way. Some handle fast motion but drift on low texture. Others handle occlusion but flip identities. So if you just roll a die and pick one, you are propagating those errors instead of canceling them out. This motivates a simple experiment. What if at every frame we had an oracle that picked the best tracker for that specific frame? The diamonds here are the oracle, the circles are individual trackers, and the black bar is random selection. The gap is huge across all 4 datasets, so the best tracker genuinely changes per frame, and static or random selection is leaving a lot on the table. Which leads to our question: can we learn a model that approximates this oracle on real videos without ground truth? That's exactly what our verifier does. Given a query point, we take M off-the-shelf trackers and let them all produce candidate trajectories. The verifier then scores each candidate at every frame and picks the most reliable one. And we use it two ways: as a pseudo-label selector during training and as a plug-and-play ensemble at inference time. Quick look at the architecture. We first track our initial query point with different trackers, essentially producing meaningful alternatives or candidates for future locations of this point. Then we extract localized visual features, both around the query point and around each candidate prediction at every frame. These go into a candidate transformer that does cross-attention across candidates per frame and self-attention across time, so it can reason about both appearance and temporal consistency. The output is a reliability distribution over candidates at each frame. We just pick the highest scoring one. So how do we train the verifier? Entirely on synthetic data. We take ground truth trajectories, apply realistic perturbations like drift, jitter, jumps, and identity switches. This generates candidate trajectories that mimic real track errors. We feed these candidates to the verifier, which gives us a score distribution over candidates at each frame. Then we use a soft contrastive loss that ranks candidates by their distance to ground truth. No real-world labels needed at this stage. Once the verifier is trained, we use it to label real videos. We take around 5K unlabeled videos from a collection of real-world datasets, run all teachers on them, and let the verifier pick the most reliable prediction per frame. Those become pseudo-labels. Then we fine-tune our student model track on 2. The result is now track on R. Data efficient and no annotations. It gives us cleaner supervision than random teacher sampling. Two sets of results. First, using the verifier as a plug-and-play ensemble at inference. The pink bars are the verifier picking among teachers. You can see it beats every individual one on every dataset. On average, 4.7 over random teacher selection and 1.8 even over the best single tracker. So the verifier really is turning model diversity into a strength. Second, the full fine-tuned model. This table shows delta average results on public benchmarks, 4 real world and 2 synthetic. Track on R, the last row, sets the state of the art. And it improves over our baseline track on 2 across every benchmark by a large margin. So our adaptation transfers well, even to settings our training data didn't cover using only 5K real world videos. To wrap up, we introduced a learned verifier that scores per frame reliability across multiple trackers. It works as a plug and play ensemble, and it produces clean pseudo labels for annotation free adaptation, giving us state of the art results across public benchmarks. This work builds on a lot of great prior research, thanks to all of these authors. And thanks for watching. The project page and the codes are linked here. Check them out for more details.